Welcome you all to the Spark Research YouTube channel. This is Dr. Virchandra, Assistant Professor in the Department of ECE. And here is another session for this course, Signal and Processing. And so this is the second and the last part of this unit third. And here we are going to talk about the analysis of the discrete time, signals and system. So in this particular session, primarily we are going to focus on the Z transform. We'll look into the region of convergence, and so we'll look into the Z transform stability analysis, and also we'll see how the inverse Z transform can be done using the partial method. Okay, so here is the outline of your session, and this is the entire syllabus for your unit third, right? So let's start. So question is that what is the Z transform? So if we will look into the Z transform, this is almost very much similar to the DFT. That is the the whatever we have done, that is discrete Fourier transform. Very much similarities, right? So now how to do? So Z transform is a very important tool in describing and analyzing digital system, right? It also offers the technique for digital filter design. So this is very useful for digital filter design, right? And how can we transform, that is a Z transform of any causal sequence? Suppose your sequence is, that this is your sequence, then how will you transform? So if you remember in DFT, we have used it in order to multiply exponential of minus j omega n. So instead of that, we are using z to the power minus n. Remaining all other terms are same, right? So x of z, you can see z, why are we telling? Because we are converting into the z transform. In DFT, we have used x of k. So this will be n is equal to 0 to infinity x of n is this is, right? This sequence is your x of n, and then multiply z to the power minus of n. That's all. As for example, x0 and z to the power minus 0, x1 z to the power minus 1. So n will be equal to 1 to the number of terms. It will depends on the number of terms of the sequence. As for example, x of n is u of n, right? So what will be the z transform of this u of n? So our objective is to find out the z transform of u of n. So how will do that? So formula is same, the same formula we are going to use it here. Okay, so u of n, instead of the x of n, just replace u of n and then z to the power minus n. So n is equal to 0 to minus infinity. So now put like u of n is nothing, 1 only. So 1 into z of the z to the power minus 1. So z to the power minus 1 and into that is minus 1. So we can write z to the power minus 1 and to the power n, because n into 1 is equal to minus n only. Now, why are we writing z to the power minus 1? Shortly, you will analyze, right? So we can write 1 now, 1 plus z to the power minus n plus z to the power minus 2 whole square, like that, right? And then finally, after adding, you will get this value. How will you get this value? So uh, GP is of, like, if R is less than equal to 1, then S infinity is equal to A divided by 1 minus R. So A is your first term, that is 1, and R is equal to Z inverse, right? So you will get the X of Z is equal to Z divided by Z minus 1. So this is the summation. So this is the final value of X of Z, that is the Z transform of U of N, right? Similarly, you can put the any functions here in this formula instead of the x of n, and you can get the z transform of any sequence, right? Let's see here another sequence, xn is equal to a to the power n and then un. So put the value here, and again you can rewrite this equation, and so here it will be a to z to the power, like that. Again use the same z, the formula in order to a divided by 1 minus r, and you will get x of z is equal to this value. So both previous and this are almost same. So another example is just, there is nothing more concept here. Okay, so now what is the region of convergence, right? So here, like suppose this is the x of z for your x of n, right? So the region of convergence will always the values of the z that makes the summation to exist form a region of convergence, right? So it should exist. If z is not existing, means the whatever we are getting the z transform, it should be valid for z. If it is not valid for z, that is the outside, means the that will not be considered as the region of convergence. So while all other values of z outside the region of convergence will cause the summation of the divergence. So that is called the divergence also. As for example, for del of n, your z transform will be 1 and the region of convergence like z greater than 0, right? A u n, so now only we have calculated, so the z transform will be a z divided by z minus 1 and the region of convergence is z should be greater than 1, right? So here you can see in the denominator, if z is equal to 1, what will be the problem? So 1 minus 1 will be equal to 0 and the entire terms will be the infinity. So z minus 1, the denominator must be greater than equal to 0. That is called the region of convergence. So similarly, you can find out the region of convergence for other functions. This table is very important one. You can see here these are the sequence and the corresponding z transform and corresponding the region of convergence. So very important all for all these sequence. You can see these are the sequence and these are the z transform and the corresponding region of convergence. You can check it in detail. So this is very important table, right? Let's go ahead. So now some properties we are going to take. Linearity, it will follow the linearity, right? Here is as for example, so un and 0.5 n to the power un. So clearly since it is following the linearity property, so no need to have the problem. You can calculate the z transform of individual these two functions and add them, right? So for u of n, already we know z divided by z minus 1, and for this part, you know, the half, you can find like this, right? So z divided by z minus 1. And now finally you can add. Here this one belongs to this and right. So here this belongs to this and this. So you can add and you will get. Similarly, the shift theorem, right? So, given the Z transform sequence, the Z transform of x n minus 1, the real, the time shifted sequence is given by Z of x n minus m and equal to Z to the power minus m. So, if you are shifting in time domain, it will be multiplied by Z to the power minus m, the amount of time that you are shifting, right? And then xz. So, use this. Here is the one problem. So suppose you are shifting n minus 5, so m is equal to how much? M is equal to 5 here, right? So just shift it in the frequency domain, like now you have to multiply by z to the power minus m. So here z to the power minus m means m is equal to 5 and then get the transform of the remaining. So this transform is very simple, already we got it, and here is the z transform of this function and then z to the power minus 5. So multiply this, right, and get the final value. So this is the one of the simple application of these properties, right? So property is very important. Okay, here is another properties. Given two sequences n1 and n2 and their convolution determined as follows: xn is equal to this and that will be equal to this is convolution for properties, right? And in the z domain you can directly multiply x1 and x2. So let's see the application. So here x1 is given and x2 is given. So xz will be the either convolution of that x1 and x2 in the time domain. So this one, and so you can get the value of x1 and x2 and then you can take the convolution. So you will get the finally transform by multiplying that is x1z and x2 because of these properties, right? So here check the properties, multiply in the z domain, you will get the final values. Okay, so this is the another application. Okay, so z transform definition. Here we are going to talk about the stability. So dt, that is discrete time system, will be stable only if z is less than equal to 1, less than like the modulus of z must be less than 1 in this, otherwise it will not be stable, and that is also called the region of convergence, that is ROC. We have already seen the ROC for the different functions, the different sequence, right? You can check it. And here is the region of convergence. So this is z is equal to 1 circle, z is equal to 1 if your poles are lies inside, right? So green color is showing what? A stable region. And outside this means if poles are outside here or here or here, that is called the unstable region. So find out for hn is equal to this, here it is decaying. So if z is greater less than 1 stable, and if it is greater than 1 means unstable, right? So this is the technique to find out the stability condition. Now we will talk about the inverse z transform. So like we can find out using the partial or the one long division method. So you can, long division method, you can divide up the numerator divided by the numerator, and then you can convert. That is the another method, but in our syllabus we will talk about the partial fraction. So very simple one, let's talk about it. So how to solve? Here is the question. Directly we will take the question. Suppose xz. So this is the z transform, right? So it is given z transform. Now what is our objective? Our objective is to find out the x of k, right? So we will get the value of the z transform. So inverse z transform, right? So let's see here using the partial fraction. So first 2 z inverse and then plus another, like we can so this is not a partial fraction, this is the simple technique. So if you know the z transform of any sequence, directly you can write, right? So directly we are using un properties, and so since we know that the z transform of this z inverse divided by z minus 0.5 of this, it will be become, so that is why we are using, right? And so you can rewrite now un, the what is the z transform of the 0.5 and to the un, that is z un, z transform is z divided by z minus 0.5, and z inverse it will be because of this, right? So if you know the z transform, inverse z transform of any functions, means if you know the z transform of 2 del n, that is equal to z inverse, then inversely you can tell that the inverse z transform of this will be this. So this technique we are using. Similarly you can use the same technique here, and you can get, right? Now we'll see how to solve it using the partial fraction method. So now see xz is here, and now this is difficult to remember the z transform of this particular function. So we can break it, right? We will break, and how we'll break? So we will break it like first xz divided by, we can rewrite this equation and break like this, a divided by first the right, like denominator and like this, and so here we can rewrite these equations and get the value of a and b. So and once we'll get the value of a and b, then you will see that since numerator z minus 1 and z minus half, so already we know the z transform of un and a to the power and un, right? So we will convert back. So get the once we'll solve the left side and right side, both if you'll equate the equations, you will get the value of a and b, right? So that a and b, a is equal to twice z you will get, and b equal to minus of z. So once you will solve, after solving you will get it, right? And once you will get, now see z minus 1, so it is nothing, u of n, and 2 is there, so 2 of u of n, this one, and similarly half to the power n and u of n. So this is the simple technique. Similarly, xn, now again we have to find for this function, right? So again we will rewrite this equation, that is equal to a plus b divided by this and this, right? So here z square is there, it means z minus half square is there. So in order to write this, this type of equation, we have to right? Z minus A and Z minus A whole square, right? Then get the value of A, B, C, and then put the values like A, B, C, and then like A is equal to, like here you will get 4Z, B is equal to minus 4Z, and C is equal to minus 1Z. After equating left side and right side, right? So this is the left side equations that you have, xz by z, that is this one, right? And right side that is unknown for us. Equate and get, and after getting you can get like now this one, and so this is nothing, the inverse z transform of un, and this one is nothing, the inverse z transform of half a to the power n un, and this one is right, and then add it because this follows the linearity property. So this is the final z inverse z transform of this equation. Okay. So here is the, the map view of your Z transform. So here is the Z transform, the the your equation. So you can rewrite this equation and get the value of A and get the value of B, that is unknown, right? And then finally you can get the values in the Z of n, right? And then you can represent in the time series. So these are the steps. Thank you to join the session. If you have any doubts, please drop your comments. Thank you.